There are other methods also to bias the bipolar junction transistor, but they are not that stable. One of them, for example, is this method here, which is called collector feedback biasing. Collector feedback biasing. Then the base is connected to the collector through this RB like this. Okay. So now, if I want to solve this one here, as I said, usually we need to find the relation between VCE and IC. It is the same idea, So here VCE, this is a voltage here, VCE. The voltage VCE equal what? Equals this voltage minus the voltage across RC. So VCE equal VCC minus this voltage, which is IC time RC. So this is the equation here. VCE equal VCC minus IC time RC. Okay, but so we use this equation, of course, to draw this line. It is the same equation here. So when VCE is 0, then in this case IC equal VCC over RC, which is this one here, the saturation current. And when IC equals 0, VCE equal VCC. VCE equal VCC. This is a cutoff voltage. So now we have these 2 points. You can draw the load line. And the next step is to do what? Is to find IC. And then after that, to substitute in this equation to calculate VCE. This is what we are doing usually. Then how can we find IC? How can we find IC? To find IC, usually you have to use the other loop or other branch. VCE, we use this one here. Okay. We know the voltage here equal VCC minus the voltage here. Okay, this is for VCE. What about IC? We have to use the other one, this one here. Of course, the current here is I beta, IP. The current is the base current, IB. Okay, so we don't know the voltage here. I don't know the voltage here. So it is impossible to just use this part here. So how can we use it? We have to use the whole part from VCE, from VCC to this one here, to this one, to this one, to this one. Okay, so this loop, because it's a ground, of course, so it's exactly as if you have a loop here. So VCC, the voltage VCC equal what? Equals this voltage here, which is IC time RC. Okay, that's good. IC time RC. Second, plus this voltage. What is this voltage? Is IB time RB. IB time RB. You can remove IB. You can say IB equal IC divided by beta. Okay, so in this case, you still have IC as a variable. So the current voltage here is IB time RB. Remove IB or and replace it by IC divided by beta. Okay, and third one here. What's the voltage here? Is 0.7 volt. So now we have one equation IC. You can calculate IC. Simple, very simple. Then let us see if we have this example here. This 15 volts, this is 10K, 180K, and so on. Then if we want to calculate or write the equation here, this is VCE equal VCC minus ICRC. So let's draw the load line. So the load line from this point here, VCE equal cutoff equal 15 volt. This is the VCC. And this point, the saturation current is VCC divided by RC, which is 10K. So it's 15 divided by 10. That is 1.5 milliampere. Then now I know that these 2 points, I can draw the load line. Now I will look for the Q point, the operating point. Then first I need to find IC. What is IC? To find IC, you have to go over this line here, this line. Then 15 volt, you can write it. Let's write it here. Select all, delete. Then we have 15 volt. 15 volt equal what? Equal IC time 10K. Right? 10K plus. The second one is IP time 180K. IP is IC over beta. What's beta? Beta is 100. Let's make it 100 first. Or let's make it just beta. Okay, so IC divided by beta time what? Time 180K. Okay, plus 0.7, of course, 0.7 volt. The voltage here is 0.7 volt. Then what you need to do is just move this 0.7 to the other side. Then it will be 14.3 volt equal. And you can take common factor here. IC as a common factor. Then you will have 10K here and 180 divided by beta. Then this equal IC like this. Time what? Time 10K plus 180K divided by beta. Then now you can find IC. Then IC equal what? IC equal 14.3 volt divided by 10K plus 180K over beta. And this will be IC. This will be IC. Okay. Then you substitute in the other equation here, VCE equal VCC minus ICR. Then you can calculate VCE. Okay. Now, when beta equal 100, what happened? This is the same equation. The same equation. VCC minus VBE, which is 14.3, divided by RC, which is this number here, 10K. RP is 180 divided by beta. So now let us see what happened here. When beta equal 100, if you substitute by beta equal 100, this is 1.21. When beta equal 50, it is 1.05. Okay, so actually here it is 13% less. Then when you actually change beta to 1/2, you are changing 13%. This is a big change. Previous one, it was 0.8%, something like this. So very small change. Here is 13%. Okay, what about the voltage, VCE? When it is 100, it is 2.9. When it is 50, it is 4.5 volt. Let us see if it is 200. What will happen if it is 200? Let's calculate it. If it is 200, then VCC is 15 minus VBE 0.7, that is 14.3. Divided by RC, which is 10K, plus 180, divided by beta, which is 200. If I make it 200, then equal 1.31. Okay, so the current here will be 1.31. So let me make it here. Write it 1.3. Oh, come on. So if beta is 200, this is 1.31 milliamp. (1.31 milliampere). And now when you substitute in this equation, then VCE equal what? IC, this IC time RC. RC is 10. Okay. And you give it a negative sign and you add VCC, which is 15 volt. That will be 1.88. Okay. So it will be 1.88. So it is 1.88. So when beta is 200, the voltage is 1.88 and the current is 1.31. Of course, you see here there is a big difference. There is a big difference between 2.9 and 1.88. There's a big difference. Of course, okay, because the difference here is almost what? Almost 1 volt. 1 volt relative to 1.88. This is more than 50%. Okay, and here that's what we have here. It's 50% more change here, and here's this 13% in the current. So this one is unstable. This one is unstable. There's another method which is called emitter feedback. Emitter feedback. So we have this resistor here, RE. So besides this one, we have this resistor. The previous one does not have this resistor. We have this RP is connected here. The other one here. So let's see here. Let's use a pointer. RP was connected here. Okay, and we did not have RE in the previous example. So let us follow the same steps. First, we need to find VCE. Okay, to plot the load line. Then this VCE equal what? Equal VCC minus the voltage here, minus the voltage here. And so the voltage equal IC times RC plus RE. Then this is VCE equal VCC minus IC times RC plus RE. Okay. Second, to plot the load line, when IC equals 0, VCC equal VCE, VCE equal VCC. This is the cutoff voltage here. And when VCE equals 0, this current, the saturation current equal VCC divided by RC plus RE, which is this one here. Then now we plot the load line. The next step is to calculate the current, this current here, IC, and VCE. How do you calculate the current? Of course, you will not use this loop here. No, you will use the other one because you will use VCE, you calculate VCE using this one. So we have to follow or to go through this line here, this loop, from here to here. So the voltage VCC equal what? Equals the voltage across RP. What is the voltage across RP? Is IP time RP. And IP is IC divided by beta. Then now we relate it to IC. Okay, and the voltage here is what? The voltage here is 0.7 volt. We know this. And what is the voltage here? The voltage here is IC times RE. IC times RE. So now we have one equation, one unknown, which is IC. We can calculate IC. So like this one here, VCC minus VB, or VCC equal this current, this voltage plus this voltage plus VB. Or you can move the voltage VB the other side to calculate IC now. And then we substitute in this equation to calculate VCE. So this is the step. So here, if we have these values, then we can first we need to plot the load line. So this point here is supposed to be VCC, which is 20 volt, divided by RC plus RE. RC is 1.8K, RE is 200 ohm. Okay, so it will be 1.8 plus 200. And VCC then it will be 10 milliampere. 10 milliampere. Because 1.8 plus 1.8K plus 200, this is a 2K. It's a 2K because it is 1800 plus 200. This is 2000. 2000 is 2K. So 20 volt divided by 2K, which will be 10 milliampere. And the other point is VCC, which is 20 volt. This is a load line now. Then we need to calculate IC. As I said, we're using this loop here. Follow this loop. Then this 20 volt equal this current IP, which is IC over beta, divided by RP, or time RP, sorry. This voltage here is 0.7, and this voltage is IC times 200. Okay, you have to be consistent here. If you use 200, you have to make all the resistors or resistance in ohm. If you use 270K, then you have to convert this one to make it 0.2K. Okay, be careful. So this 200 here is 200 or 0.2K. So if you use 270K, then you have to use this one as 0.2K. If you use this one 200, you have to use this one as a 270,000 ohm. Okay, to be consistent. Then you calculate IC using this equation. Okay, when we beta is 100, this is the current. The current is 6.6 milliampere. When beta is 50, it is 3.45. You see, there's a big difference between them. It is almost 50% change. Okay, what about the voltage? Of course, we need to substitute by these values here in this equation. When beta is 100, 6.68. When beta is 50, is 13.1 volt. Of course, there is a big change. It's almost 100% in the voltage. So again, this method is unstable. There's a the third method is the third method from this type. We have two methods before. The first one, when we have a positive voltage and negative voltage, positive VCC and negative VAE. Second, when we have this voltage divider R1 and R2, we use Thevenin equivalent. And then the third, when we have this feedback, we have two feedback now. This we call the emitter feedback, and the other one was collector feedback. And emitter feedback and collector feedback. The third one is a combination between them, and we have both at the same time. See, RB is connected here now, but we have this resistor. So now if you want to write the equation for this circuit, again, it is the same steps. What is the voltage VCE? What's the voltage between these 2 points? Simply, it is VCC minus the voltage across RC minus the voltage across RE. The voltage across RC is IC times RC, and the voltage across RE is approximately IC times RE. Then VCC equal VCE equal what? This voltage VCC minus the current IC times RC plus RE. Then this is the equation that we use to draw the load line. And it's very simple to draw it when VCE equals 0. If VCE equals 0, then IC equal VCC divided by RC plus RE. This one here. This is the saturation current. And if the current is 0, then VCE and VCC are the same. So this is the cutoff voltage here, cutoff voltage. Then next we need to calculate IC, and then from this equation we calculate VCE. How to calculate IC again? We have to use another loop, so which is this one here. Okay, so let us see. This voltage equal what? VCC equal what? Equal this voltage, which is IC times RC, plus this voltage, which is IP times RB. IB is IC divided by beta. So we have to find it in terms of IC. Okay, then plus this voltage here, which is 0.7 volt, plus this voltage, which is IC times RE, approximately. Okay, so now we have one equation in one unknown, which is IC. You can calculate it. So this was the last problem. Okay, after that we have this homework, which is problem 1 and 5 and 13 in the book. You need to solve them, and if you have any question, you let me know in the live lecture. For the first problem here, this is similar to the first one that has VCC and negative VEE. You have a positive voltage here and negative voltage here. The second one, this is, you can solve it using Thevenin equivalent or just approximate value. And this one is a common, this one here is a common what? Common collector here. This is a common collector circuit. Okay, so you just look at the examples and try to solve this. You plot the load line first, and then find IC, then find VCE if beta is 100. You will find some more examples here in these slides for some other problems, like this one here. These are just the solution here, the solutions for this one. So you will find the solution after that, and you will find also some problems with P and P. Okay, this is P and P. Since they are the same, it is the same concept here. I will not go through them. You just need to remember NPN, and of course it will be easy for you to understand P and P. Okay, you have two examples here about P and P. But remember that the answers for these three equations are in the slides. So you need to look at them carefully. Try to solve them first, and then after that, if you have any question or you can solve them, look at the answers. If you can't understand it, also still have the live lectures. You can ask question, and I will explain it to you. Thank you very much for watching, and see you in chapter 6. Goodbye.